Just a second, I'm trying to set up my Zoom on my Surface so that I can. Can you allow me to share my screen, please? I've joined with two IDs, both Sujit Roy, allow both of them.
Yeah, you are good to go.
Looks like it is working fine. Okay, so you guys can hear me, I assume. You can talk to me as well, wherever you feel like you have a problem. Okay. The objective for today's class is to look at support vector machines, which is SVM, and understand mathematically. What we were trying to do yesterday was how you will do the minimize the function, what you have to minimize for subjective function, and all that. Let's see. So what we have to study today is SVM. And so let's consider that you have this, there are some negative signs here and there are some positive signs here. Everybody here, I just want to check for few people. Okay, right. So you have this thing, which is you have some samples given as negative, let's say, and some samples given as positive. Let's say that I try to, you know, divide this line just with some of the dotted points. And now what I want is, I want also to look at this point is that what could be the maximum width that we can take. And let's say I try to divide again the sum of the things, which is, let's say this thing is, we have these points. Okay. So if these were your different combinations, plus plus and minus, and you wanted to take out, separate them. So what we can also assume is that there is a vector W here, which is the difference here. So you can project that on to this plane. And then there is some unknown part here, which is lying exactly on this boundary. So we are trying to see the boundary here first for both of them. So it is lying somewhere here. So I can say that according to this vector as well, that you have some unknown vector here. Okay. So if I try to find out the projection of this vector on this one, we can easily write it. We remember from our classes that we have W vector, but the vector, it should be greater than equal to some constant. Okay. So now if it is for your positive and it is for your negative, So we are trying to do that. So let's say that we're trying to make a decision rule here, and we replace that C with some minus B here. So we can also write the same equation as U vector minus B greater than or equal to 0. We can write this, right? So if this is the case, then it will classify the positive point, right? So this is your first decision rule. Okay. Now what are you look? We're trying to look at this quantity here. Okay, so we try to look at this quantity here, which we are trying to work at. So which is, so this is greater than 0. This quantity is greater than or equal to 0. So also if I try to look for sample, for positive sample, let's say that this is some sample X here. So for positive sample, I can also rewrite it again as vector for X for positive sample, and then plus B, sorry, this will be plus B, no? Because we have inserted minus B into the, so if you turn it like this, so it will be minus C, so it is equal to 0. So it's basic algebra that we're doing. So plus B, this will be greater than or equal to, let's say that the distance is we are trying to do is 0 at this point and 1 unit on both the sides. We're trying to get to the 1. Okay, so this is maximizing the boundary. So this is another equation that we have done. So it is for positive samples. Similarly, for negative samples, we can write it negative plus B greater than, but it should be less than or equal to minus 1. Okay, so now this is a third equation. So when we look at, so we are trying to do here is with deciding the boundary. Now we have these two equations, which is 2 and 3, right? So we have these two equations, so we can combine them into one equation. And now how we can do that? So we can introduce some variable here, which can take into account the variation in 2 and 3, because if it does positive and negative sample, we don't want to work with two different equations. We can merge both of the equations by introducing a new variable. So let's say that I try to introduce a new constant here. So that constant can be y of sub I, right? So this y of sub I, this will be plus 1 for positive samples, and this will be minus 1 for negative samples. Okay. So now when we try to rewrite equation 2, I can rewrite it as, oops, sorry. I can rewrite equation 2 as y of sub I xi vector, since it is a vector. So if I just forget some time, consider them a vector, greater than or equal to 1. Similarly, equation 3, we can write it as y of sub I, keeping it is the minus 1. So it will be now, if you substitute it, it will be again xi p greater than or equal to 1. Okay, now you see that both of them are exactly same. So let's mark it as one of our final outcome of this equation. Okay.
But
Now,
what was the significance of the first equation where we said that for any u we have wu plus b? I mean the dot
so
product
this is
B.
trying to, we're trying to projection. So like you say that u is some sample which is lying on this boundary, you know, this area, right? Let's say consider the street, right? Lying
Right,
some boundary.
in that strip, okay.
Yeah, in that strip, and in this street or strip. So in the street, you're trying to project this onto the plane. So
Right.
it's a simple vector decomposition that we do.
Right.
Okay. So when we go, So we try to project it on the line and perpendicular.
But then if equation 3 says that for all negative samples we have its value as less than equal to -1, so that's basically below any number on left of the bottommost boundary, right?
Yes. So negative is here, as we draw, and positive is here. Yeah.
So in that strip, we don't really have condition 1 as necessarily true, because there is a range where the value goes between 0 and -1.
Yeah, we're trying to, when we try to project it on that space. Yeah, that's true. But initially, you see here, the condition that we chose was 0, right? So what our objective is that we do not need to stick on this line, which is this line. We want to maximize it, right? We want to create a separation between two different classes. So we want to maximize it. So at least we could take a unit difference from the center point. That's why we are using 1 here. So it's just a simple constant, no? It is where we're taking like +1 this side and -1 this side. Okay.
Okay. Go ahead.
Right. So now when we have this equation, which is y of sub I, then x of sub I into w plus b is greater than or equal to 1, we try to bring it this side. So it will be y of I and x vector of sub I into w vector plus b -1 greater than or equal to 0. Okay. So let's also try to figure out, since we are trying to find out for the sample which were in the middle of the street, so we can remove the term which is greater than 0 and greater than or equal to 0. We can just write them as y of sub I x vector of sub I into w plus b -1 is equal to 0. Okay, so this is fifth equation that we have. So it is just simplifying it further. So now let's come back again to the same drawing that we were doing. So we have, so we try to draw some samples here, negative, and then here were some positive, okay, or make it like this, positive. Now we try to draw the same thing. So let's say that you had 1 here and then 1 here. Okay, so now from origin, if you try to find out, so there is a projection which you will be doing here, and there is here. So for the negative sample, right? So if I want to find the difference between both of them, so let's say that this was x of negative and this is x of positive. I try to find the difference between them. We'll just try to find this one, which will be x plus minus of x negative sample. So this will be your width, right? So this will be your width. So this is, now let's also assume that we have a unit. We can also look at this thing that if you have a vector projection in this angle and we do the normal projection, normal vector on this thing. So we can take that normal w and keeping that convert it to a unit vector. So you can write the width as x plus minus x minus, and this will be a dot product with w by the magnitude of w. This will be converted to a unit vector. Now, if you look at this x plus, okay, and x minus, and now we look at the equation that we were doing above. So if you replace for the sample in the middle of the street and y is equal to 1, right? So if your y is equal to 1 and the sample is in the street, so x I or of w will be equal to 1 plus b, and similarly for negative it will be 1 plus b, and for positive it will be 1 minus b, because you will, so this whole term. So for x plus, I can again write it as 1 minus b, and this whole term can be written as 1 plus b. So this whole equation has broken into very small parts. So now when I try to again analyze it, this whole thing can be written as x positive minus x negative dot product of magnitude of w can be written as 2 by the magnitude of w So this will become the width of the string. Now our objective is to maximize this term, right? So we have to maximize, because we are trying to increase the width, we're trying to maximize the 2 by w. So when we are trying to write that we want to do the maximize of 2 by w, we can also write it as we want to maximize 1 by w, right? Then you can also write it that you are trying to minimize w, okay? And then just to make it a bit simpler, you can also write it as that you're trying to minimize 1 by 2 of w squared. Okay, this is just for mathematical simplification when we are trying to solve the equations. So when you are trying to minimize this thing, so we want to find out the minima now, right? We want to find out the minima for this specific function. So which sort of equation do you think will fit in? We have seen many of the equations for minima. You have Legendre, and then you have Laplace, you have Lagrange. So for this one, since you guys are not talking, so we will use Lagrange's function, right? So what we want to do is we want to minimize this, and so I can write it in the form of Lagrange by, so this will be half of what we have minus, it will be a complete summation over, I'll introduce a new variable, which will be the factor multiplication, which will be alpha I. Okay. And now here we will have the full equation, which we just wrote before. So, okay. So just write it here. So now if I try to write it, so I have to get the full equation here. So from here, which is yi xi w plus b. Okay, so minus 1. So I'll just put the same equation here in the Lagrange, and we will be yi by w vector of x vector plus b, and this is the full term that we are trying to take the minus 1 because it was opposite side of the 1, and so that will be it. Okay, so this is what we are trying to do here. So this will act as our constraint. Now, so when we have this equation, so we're trying to minimize it in order to look at this one. So we are trying to get this whole thing for an optimum performance. Let's not go for minimum or maximum. We're trying to find the extremes of function. So what we're trying to do is actually present it in a Lagrange equation and then trying to solve it. So how can we go about it? So what we can do in one way is, we have seen in Lagrange, one we can do is we can take the partial derivative with respect to w, and then we'll take the partial derivative with respect to b. So if we take the partial derivative with respect to w, I can write it's a vector, so we will have to just unhook all the components and then use it as a scalar and then put it in. So when I do this whole part, we'll try to do with this whole part. So firstly with this one, so it will come across, it will deduct it, so we will be just left with the w. Then you will have minus of this term, and then we have a w here, which is yi multiplied by w multiplied by x, right? And then that is multiplied by alpha I, right? So this is another term that we have here for this partial derivative, which is interacting with w. So this will be minus sigma, and then it will be alpha I, then you have yi, and you have xi. Okay. So where yi can be, you can have this is plus 1, minus 1, which we are doing before. Okay. So Let's not go into it for simplification. So this is with respect to W. And then when we are trying to do it with respect to D, we will do the same thing. So in this term, we have D only here, which is getting multiplied with alpha, and we have with W, sorry, Y. So we have this thing, and yeah, okay. So with Y, so now we will have this term, which will be just partial derivatives. It will be minus sigma alpha I yi. Of course, so D will be not there, and this will be equal to 0 that we are trying to do, right? So we can also write it as sigma of equal to 0, and then we go ahead that when we already got all these values, which is here, this so one value that we have got is this thing, which is dl by dw, which is w minus alpha I yi xi. So if I want to write this and this is equal to 0, I can write it as w is equal to sigma running from I. You have alpha I, yi, and xi. Okay, we'll keep a note of this equation. I forgot the trend where we're going. So let's take it again as equation 5. What where we were. So equation 5. So I'm lost somewhere. Forget it. So now we try to plug this back into the Lagrange's equation that we had here. So we have W here and W here. So what we are going to do is we're going to plug the values of W and then expand this whole equation. So just bear with me. I can understand it can be a very big equation to handle, but you look at this thing is when I plug this in, so I can make it as, so I can, but wait, I'll write Lagrange equation just here for the reference here, very small. Or are you guys making notes with it so I don't need to write it again? I don't know. So L is equal to half. This was our equation. W square minus sigma alpha I multiplied by yi. And then you had vector x, I vector minus b, and sorry, plus b minus 1, and this is. So when we plug back into this function, we have the value that we have. So we got the value as w is equal to this thing, right? So alpha I yi xi. So obviously in the first case it will be very simple. So it will be L is now can be written as half of sigma. So sigma alpha I, right? Then you have xi, and then yeah, yi and xi. Sorry, I got divided. Yi and xi. Okay, so this is what we got, and then we are going to take the term with the dot product. Now we have this thing which is square. So we will be having this with the dot product, which will be again sigma of x. Alpha and x looks both of the same. Alpha I, yi, and xi. Okay, this is what. So we'll try to keep a different parameter here, so not to get confused. So let's keep it as j. Okay, so that we have two different xi, yi, xi. Then alpha I, yi, xi, and then you have alpha j, y sub j, and then x sub j. And now we do the other term, which is this one. So it can be written as this thing, and then you have sigma, and it will be x sigma alpha I y sub I x sub I, and then dot product with sigma alpha j y j and x j, and then you have minus sigma alpha I yi b plus phi sigma of alpha I. Okay. So this is what we will get. And now if we look at the whole equation, there is only one point where we have the constant, and this is the constant that we will have it. So we can just rewrite this whole part as this thing minus p sigma alpha I yi. Okay. And since this is a constant and this is equal to 0, so this whole term will be equal to 0. Okay. So we saw that somewhere here. Okay. We saw that here. Now, so we have done this, and now, so if we just simplify it, taking the common terms, so we can, so what we are calling is we can always take, so we will just take this function here and we'll use it first. So I will just write here sigma alpha I, and then minus of half taking, and then can run for sigma I, then sigma j, and it will be alpha I, alpha j, y of sub I, y of sub j, and then you have x of sub I and x of sub j, and that vectors. So, okay. So now when you look at it, when you try to maximize or minimize or find extremities, what it's dependent on is we have only this vector decomposition, isn't it? We have two vectors here. So we are looking at these two vectors in order to find the optimization, right? So this optimization is completely dependent on these two vectors, which are xi and dot product of xi. So now let's again, so if I try to solve it in a, put all of them into the decision rule that we draw in the beginning, and so if I try to put them in the decision rule, we can say that it will be sigma alpha I y sub I x sub I by u vector plus b greater than equal to 0. Then this is the condition true for the positive samples, right? So this is the condition that we got, and so this whole system can work perfectly fine if you just make a program on it, completely perfectly if you work fine for all the linear samples, right? Because we have been dealing with the linear sphere and other stuff, linear samples. So in order for it to work with say space which is not completely linear, okay, so let's say that you have somewhere this space, so you have two same class here, and then you have two classes which are here. Now obviously this is not possible for us to separate this linearly, so we might need something. But if you look at it from this point, that if I connect these and I try to find a projection of this one on this thing, and similarly projection of this on this thing, so now we see that we can create a hyperplane, which is subplane or projection thing. And when you project that into a new transformation thing, then we will be able to transform our data and it will be separable. That's why in machine learning or any other space, when you are looking at the samples and other things, many times you will be able to see that when we are transforming or when we are doing this thing. Sorry. Yeah, when we are transforming or when you are doing this thing, it is very much, it is preferred when you transform, it becomes separable or something. So let's say that this whole separation thing and transformation is represented by a new sphere, which is phi of x. Okay. So now you require, what you want to do is you just projected it. So you want to maximize phi of x, sorry, phi of xi, and then phi of xj, right? So this is what you're trying to maximize. So for this, you are trying to find, so you're trying to identify something which is dependent again on xi, and then so what should we do in order to do this thing? So for here, then the story came up like, if what will happen, like if I make a new function, right, which can take care of this projection, then I should be able to get all these samples. So what I can do is, like, if I write a let's say if we write a new kernel, which is, let's say, z, and it is like, it will take care of the xi and xj. So it should be equal to phi of xi and phi of xj. So here come the here was the concept of kernel that came up. So then we were trying. So the mathematician tried, and then we had different kernels. I think we can look at the kernels later in some other class. Today we just focus on this thing. Then we have, let's say we have a linear kernel. So linear kernel can be written as u to v vector plus 1 raised to the power of n, right? And then if you have some polynomial kernel, or you need, so there is another kind of kernel. I'm not saying it's polynomial, but there's another kind of kernel that you can use, which comes as e raised to the power minus magnitude of xi minus xj by sigma. And if this sigma is, so this is another kernel that you can use for the functions which are for the graph that we were looking at, where you had the data points separated like this, and then you had the data points like this. So it would be able to, create a decision boundary function which are non-linear for non-linear domain. If one more thing, if your sigma is very small, which is like if sigma tends to 0, then you can see that this will go to infinity, and it will be a problem of overfitting. Okay, so there can be a problem of overfitting by the sigma. So we have to keep a note of this thing. So this whole thing came into picture looking at, so this is what we were trying to do when we were trying to create a decision boundary and trying to understand the whole thing, which is in the SVM. Okay, now, so we were trying to, so what we're trying to do is like the maximization. What we have learned is the maximization only depends actually on the dot products. So this was, so it's a bit of a story that I, when I was attending the lecture online, I heard it. So, so this whole thing was proposed by a Russian professor, and it was a master's thesis that he did. It was Vapnik, and he did in his master's thesis introduced some of the support vectors, and he looked at it, and he said that, okay, so when he moved to USA and he was working on this thing, so he said, so neural nets were coming into the picture, and he was unable to understand, or you can say not unable to understand, but he thought that neural nets are not going to work that much. It's not that good. We proposed that, so we were working on the problem at that time was handwriting desert recognition. So he said, my SVM can perform much better on it, and you have to try it. So there was a bet on that thing with the professor, and then some of them tried it, and it proves to be better. He also submitted the paper on this, on Murips, and all of them got rejected. But later on, after some years, people came to notice that the importance of support vector machines and how it is going to help. Now, for this optimization algorithm, sometime it would be we have been able to see is this thing. For this optimization problem and other stuff, we have been using gradient boosting and other stuff. So we might look at that when we are doing this thing, which is boosting algorithm or something else. So we'll not try to go on to the deep of that one today itself. So just we can say that if I try to say to you is in the terms of maximization, you want to try to minimize or something, which is a related term that we were doing is yesterday. So you can always write it as minimum of belong to the real, and then you have this thing which is w squared plus cost function, which is I running from I to n, and then you try to maximize 0, 1 minus yi of f of function itself. Trying to do something like this. So this becomes your regularization term, and this becomes your loss function. So we will study this more in when I will be covering neural nets and other stuff. So optimization, gradient boosting, and other stuff. So it would be more helpful in those scenarios. So this would be it for today's class, as we only were here to discuss this thing, which is neural net. Understanding the mathematics behind this PM. I hope it is clear, and then it is fine with you guys.
Can you share the screen? Kind of lost you at the end. So.
Okay, you want me to share again?
Yeah, just a few points at the end.
Mm-hmm. Yeah.
So basically, just before we started talking, just before we talked about kernels, can you scroll up a little bit? Yes. So we plugged in everything in the Lagrange formulation, and then we talked about how it's the xi.xj that's the key factor over here. So,
yeah.
And then this equation that summation of alpha I yi xi dot w plus b is greater than 0. What's the argument that leads to that?
So this is the same equation that we did for decision boundary, isn't it?
Right. So for each individual sample, each individual sample, this value of x dot w plus b is greater than 0. So for the sum, it will be greater than 0. Is that the argument?
Yes.
But then we also have alpha I added to it, right?
So alpha okay. So alpha is a quantity that we said when we were designing the Lagrange function for multiplication of it. So it can be, you can say that it is a scalar quantity that we are considering. Yeah.
So does it have? So is it non-negative?
Yeah, it is non-negative. We can go for negative as well. Not
because otherwise alpha I xi need not be dot w plus b need not be greater than equal to 0.
I see that.
So I think alpha should be greater equal to 0 because it was a non-linear constant.
Actually
it's
alpha
it's a linear constant that we are having here.
Constant, sorry.
So this condition will only be true if alpha into y is always positive. Otherwise, we'll have to supply some additional clause to support this statement.
Yeah.
Only if alpha into y is positive, then this holds that simply each individual term is positive, so the whole thing will be positive. So for all the negative samples, alpha I will have to be negative so that the product is positive, and then this holds. And all the positive samples, alpha will be positive, then the product will be positive.
Yes, you can say that.
So there's something missing here in terms of how we are forming this statement.
No, actually, when we form the statement here in the terms for this thing, which is substituting the value for the w here, which we calculated from the Lagrange function, so which we're trying to minimize, right? Isn't it? So we are looking at, so when we are looking for the positive samples, so we are looking for the positive samples here. So we are, and then, so this whole thing should be greater than equal to 0. So this is yi xi will be having, yi can be plus 1. Alpha will be positive, isn't it?
So basically we had an equation, then we set its two derivatives to be 0, so that it's minima. And then I don't follow you when you say that, we are looking for positive xi's. I mean, up until the derivative, setting the derivative to 0 is very standard, definition of a minima. Assuming that it's a minima, it could be a maxima, but we are saying that it's a minima. We know that. But then, why are we, talking about positive samples suddenly? It's actually, it goes both ways, right?
It will go both ways, no? That was the I spoke about, no? It can be plus 1 and minus 1.
So basically, my point here is that I understand how this and the Lagrange minimization works, but I'm not sure how we are taking that and then writing down everything that follows it, which is I don't know. It's just not clear to me at this point. Okay, let's go back a little. So I had the two derivatives. I set them to 0, and then I used them. I put that back into the longer equation. Then I use constraint number 6 to set some terms to 0, and my constraint 5 has already been used. We basically plugged it back into the equation.
Yes.
So what we get is essentially we do not have W anymore. What we have in this equation that is equal to 0 is a bunch of xi's, xj's, yi's and yj's, which we know are dependent based on xi and xj. So what exactly do we get when we equate this equal to 0? What is the unknown that we find out finally as a result of plugging back equation 5 and 6 back into equation L? What do we solve for when we plug that back?
So what we were trying here to, so what we're trying here to, we were trying to find out the minimization using the Lagrange, and then when we put it in the decision boundary, we try to look at the decision boundary in terms of if we can use the decision boundary in order to linearly separate them or not. Okay, so this is going to help them for linear separable. That is correct. And then since we are trying to deduce something, we will be going for the complex one, which is the projection matrix. Okay. I'm unable to understand the question actually.
So my question is that once we plugged everything back in, and then the equation that you have circled, right? Just above it, we get the formulation that is that involves alphas, y's, and x's. Now my x's and my y's are known; they are data points. What I have remaining is alpha i's. Now what you are saying is that in some ways we plug this whatever information we have here, we plug that back into our initial formulation, which was the definition of our decision boundary, and then we say that it will help me determine a W, right? But the initial formulation is as what I opened with was that it is dependent on my choice of alpha i's. So there is something, alpha i's have to satisfy certain criteria so that this circled equation can hold. Otherwise, it wouldn't satisfy.
So you agree to this equation that we had is, let's say that yi, and then let's say that we have w, and then you have xi and plus b, and it is greater than equal to 1. And then you introduce something which is, let's introduce the term which is for providing a regularization or something like that, for optimization, right?
Right.
So we have, so the optimization problem that we are able to see is actually was this one only, no? The optimization problem that will become from here will be the minimum that it will be having. So it will be minimum of what we're trying to do will be for, and it comes back to the same thing with the cost function, and we have then this thing that the term that we have introduced now, I and then we have I. So then you see becomes your regression parameter, which you can say that case of, which can be, it is allow small constraints to be easily ignored for larger margin, and when it is higher, it is hard to ignore, so it will have a narrow margin, and when it is infinity, it will be it will enforces all the constants, which is the hard margin. So
But
it is the
now we are
now.
adding information. I mean, like, you're going ahead. My doubt was much more
Oh,
basic
okay.
than that. No.
Okay, okay. So
Yeah.
let's try this thing that. Mm, so let's try this thing. Uh, the truth factor is I'm unable to understand your question, and
My question
so
is,
let's yeah.
How do I solve the equation for L? What do I, once I have L is equal to summation L5 minus half double sum, and then I have a decision boundary condition which goes L5 I xi dot W plus B is greater than 0. I have these two equations, and
you put them into your program for deciding the decision boundary.
And I solve for, what do I solve for at this using these two equations? Do I solve for W? Do I solve for alphas? And what is the unknown here?
You're solving for W here, no? Because we're trying to maximize the width. We have always been solving for W. It's like trying to create a decision boundary, which is going to be for the projection vector.
Okay,
so P will become a scalar quantity, and then trying to maximize this whole term, which is W by the U projection plus P greater than equal to 0.
Right. And okay. So here's another thing that I'm confused about in doing that. So that serves the purpose of my circled equation. Now, what my L says is L. What does my L supply here? L is an equation, right?
So
it's an expression right now. It's an expression. So
what
so information does it?
So Lagrange's was we used in order to find out the minimization problem, isn't it? We're trying to minimize the equation that we had, which was here. We were having, I think, so we had this constraint here.
You're basically minimizing W square.
Yes. Yeah. So we were trying to minimize the W square, and then we had the L here. We had the constraint, and then we went into plugging in all the values of W into that, and then we have this thing. We resulted with the L, which is the output. Solving the L for and trying to minimize this. So there is only two vector quantity that we were able to identify, which were xi and xj. So the minimization problem we tried to find out was this thing, what we were trying to do, that it depends on this one. So we try to minimize this thing. So it's like you can say it's a, will it be correct if I say that it was done in order to find the optimization and looking at, it depend on these two vectors only. So this thing that we can derive from this equation probably, if you are trying to ask what does it mean to have this equation, why are we using Lagrange's to do that?
And secondly, when we're talking about non-linear kernels, we're still dealing with the standard definition of dot products, right? We're not going into.
Okay, so we did, so we did not go on into the other space of the kernels. We were talking, so we tried to do for the linear, and then I introduced the concept of the kernel here. So for non-linear space and other space, we will have to go into, there are a few other loss optimization techniques that we'll have to cover. And stop sharing, and then So there are a few other optimization techniques that we have for the convex function and for the other function of how we will be doing to optimize it. So for that, we'll use borrow some concept of neural nets or optimization. So I can tell you that straight away. It's like the same thing that I just wrote after that, because the variation is a loss function. That was the constraint of optimization formula that was obtained. And then you can do the convex function optimization using the gradient descent algorithm. Or so for that, we'll have to consider the gradient descent. So I was thinking that once we do that gradient descent in the next class or
No,
something, it will
that's
be
yeah,
easier for
that's okay. I mean,
yeah. So
fundamentally, the idea remains the same.
Yeah, so my purpose was to explain you the idea behind it, because once we cover the gradient descent and something else, it will be very easy for you to understand the minimized problem for the non mm, non-linear space where you have the find the minima of a polynomial or something like that.
Okay, fair enough. So, okay, one last thing that I want to ask, which is that if my definition for this minimization problem is so fundamentally based on dot products, we said that explicitly we want things to be that xi dot xj is something desirable. Yeah. So then, how did we end up with kernels that are exponential? Wouldn't I prefer to go with things that are vector based?
So in the kernel, also polynomial kernel, we used xi and xj, no? Didn't we?
Yeah, we did, but okay, but does e raised to power xi minus xj by sigma?
By sigma, yeah.
Does it relate in some ways to dot product? I don't know. I mean, I don't know. That's why I'm asking.
Oh, okay. No. It's not a problem actually. So if somewhere relates to dot product, I'll not say that somewhere relates to dot product. It is an already defined kernel. So this is a defined kernel that we were looking at in the terms of linear, and this is the defined kernel for. Sorry, yeah, for the linear kernel you have this definition given, and then for the polynomial kernel we have this one. So it's already defined one in the terms of the vector space, where you have the x I and xj, you can consider them as the support vector. So you can take that, you can convert them all into the, the support vectors completely.
This thing is basically, it looks like a Gaussian. Norm of that is square.
Okay,
basically.
So radial basis function or.
Right. So it's basically a Gaussian based on distance between the 2 points, because it's difference and then something like that, right?
That's it.
Okay.
So I'm like, there are concepts related to primal and dual formulation as well, but I was not aware of how many people are aware with.
Yes, actually, I had noted it down when you talked about it yesterday. I couldn't read up on it. So.
Yeah, so I was not. So I can do it some other time as well with doing the primal and dual problem, but that will be a complete mathematical course that we are going to follow. Then it will be very in terms of like primal version of the classifier. So for example, that I just want to give you a getting home note that when we try to do the primal version, so we have the primal version of the classifier can be written as w vector x plus p, whereas the dual version can be written as fx.
But we use both of them, right?
Yeah, we use both of them. So when you will be going for the formulation, you will come to understand that you will be just left with the summation over the function which can be represented, but we have already done alpha I, yi, xi, x plus p. So
when you work with fluid dynamics, we have this kind of a situation where there's a strong form of the equation and then there's a weaker form of the equation, because your primal thing is an absolute thing, and
primal is like it can give you a solution or not, maybe, but dual is going to give you one.
Right.
Compulsion to give you one.
Right.
So that's something. So we can, do the primal derivation and dual derivation as well, and into the transform feature space. But I am it is in a different transform feature space, and then we can see what it is there to learn from that, which is your when you introduce your kernel trick or something. So if can't I say, okay, so just I'm just thinking, I hope, yeah, people are over time. So if somebody is thinking that they're not entertained with it, so you are fine to leave. There we don't have anything new to discuss. But yeah, so I'll just come up to this equation again, which we were discussing here, which was this one, right? So we're discussing this equation. So here I can actually introduce the kernel, isn't it? For the learning, when I'm trying to do this thing, I can reduce this whole thing with k of xj, oh sorry, xi and xj.
Yeah. Yes.
So then it becomes a kind of function, and now you have an optimization problem. Does that solve your answer if it was from the beginning? So there comes the kernel trick in the terms of two different space. So it can be like construct, it can learn and apply without explicitly computing that we're trying to compute phi x or something. And so there are different kernels. So you have this one. So Gaussian kernel that we have already seen, which was here. And so this was the Gaussian kernel that we, the 2 sigma square, sorry. So this will be your Gaussian kernel, and I'll do this square. And then we have polynomial kernel. So polynomial kernel can be anything that I think you guys be able to know. A polynomial kernel can be written as 1 plus for d greater than 0. Right? So this is polynomial kernel can be written as.
Wait,
so it can be polynomial
like your linear.
D. What?
But your linear kernel has the power n. So it's
so it's like if you combine with the, so if it is equal to 1, it becomes your linear kernel. If it is greater than 1, then so n is equal to 1, it will be your linear kernel. N is greater than 1, and then it will be your polynomial kernel in simpler fashion. Okay, for a different feature space and other stuff. Okay.
And phi is simply a transformed variable, right?
Yeah. So phi x is like just transforming it into a different space.
Right.
Okay. That's why generally we use phi here. Okay. I wish I would have some of the. I'll try to collect some of the examples. Okay, and I'll drop them in the terms of how with the kernel change it is affecting our this thing, our decision boundaries. I'll try to. There was some lectures from the Oxford. I'll try to look at some of the PPTs. Okay, and I'll drop it in probably in Slack, and you guys can look at those figures and in the different kernel space. And if you have any other questions on that one, something to discuss, we can always discuss.
It would be nice if we actually implemented this L equation and decision boundary wala equation and saw it work. That would make things a lot clearer for me, at least.
That would have made things clear, but it would be very difficult to cover all of them, in this period of time.
Just take 10 data points, and then it doesn't have to give a great fit. We'll engineer it so that it's a nice straight line. That's the decision boundary.
There should be. Let's look for some of the toolboxes. There are some toolboxes which you can use for plugging in this equation and other stuff, and then we can probably try that out. I think you said you are from fluid dynamics, so you might have some toolboxes, for plugging in this simulation.
Yeah, but I don't work with this kind of optimization stuff. It's
okay.
It's more partial differentials. So.
Okay. All right. So then that would be it if nobody else has a question. Okay, somebody send me privately. Have you tried debugging the last code? Mine also is showing dot not found in path, even having script installed 6 and from 6 imports string IO. Yes. No, I did not get a minute till now. Still have not my lunch yet. So I've not tried that. So this is a note for TAs. Please look at the code for yesterday and try to solve it why it was not working for some of the people. especially just look at the graph bridge plot, why graph bridge is not getting initialized. Okay, so that would be it for from my side. Anybody else has any comments to make? There's so less students today in just 2 hours in mathematics. That's why I do not for mathematics, the lectures. Right. Okay. So that would be it. Then thank you very much for your time. Have a great day.